half of the hour or so. We'll be done before 10 o'clock.
So we can do
We can work on our lab.
You can ask me a question. Work on the lab, yeah, good idea.
the lab that doesn't exist?
Yep.
I'm always.
Wait, where is everyone?
Okay, there was a question on the homework, maybe both of these questions, where it asks you how many orbitals can have the designation, and then, like 5p. Well, 5p can have 3 orbitals. There's 3 lines next to 5p. But then they gave you 3d with a little subscript z squared. Remember that one?
No.
Yeah.
If you did the problems, you remember that. If you look back to the pages where they were describing what orbitals are and how they're arranged around the origin of a 3-dimensional graph, you see that the p's, there's a p along the x, that would be p subscript x, a p along the y, that would be p subscript y, and then a p along the z, that's pz.
Oh, so if it says like Z, it's in one orbital?
Yes.
Okay.
The d's, there's 5 of them, and that is going to have, each of the 5 have their own designation, depending on how they're arranged about the origin. There is dxy, there's dxz, and there's dyz, and then there's 2 more. There's dx squared minus y squared, and then finally dz squared. So that's what this is talking about. It's talking about one of the d orbitals. You're looking at me, I know that one. I need that book again. Oh, you go back there. Can I borrow? Yes. Yep. All right, take a look at these. Oh, no, those are F's.
No, I get it. I just.
You don't get it.
Oh.
Look, these are the D's. If I can zoom out a little bit, there's 5 D's in every sublevel, or in every D sublevel. 5D over 1, 2, 3, 4, 5.
Yeah.
And each of the orbitals have a name. And they are. The first one is dxz. See it? And then dyz. And I'm talking about right there. dxy, dx squared minus y squared, dz squared. So that represents one orbital, dz squared does. If it just says d with no designation after it, that means all 5 d orbitals. But if it says d with a little designation, that means one specific d orbital. Oh, don't worry about how they name them. You got to do the calculus for that.
What?
You don't have to do that.
Yeah.
All you have to do is recognize that if you have a D with a designation after it, that means one specific orbital.
And then we just go look at it.
No, just say, well, that's one orbital.
It's never going to ask you to name it.
Yes, Farouk?
That means if it's dz squared, there are 2.
You can have 2 electrons in that one orbital.
Would it be possible to have an electron in there? Like dz?
There's no DC. Yeah. An orbital, remember, can hold 2 electrons. The designation is, part of the Schrodinger solution, which you don't have to do. That's making it easier for you. You're like, give me this, oh gosh, I don't get this. Yeah, you do. No, there's a P with a designation or a D with a designation that represents one orbital. Yes. All right, Spencer, would you hit the blue button over there to make it? Yeah, green. No, other one. That was it. Thank you. We have 2 properties left to talk about today. They are atomic radius and electronegativity. And then I have a bonus concept for you, and that would be the size of ions. How does the size of an atom change when it becomes an ion? It loses or gains electrons. What? It might be. No.
Atomic radius wasn't in the. There was one atomic radius problem in the question.
Yeah, there's not very many. Farouk?
Are you going to give us any trivial questions about those scientists?
Now, the quiz is just from the problems in the book.
Okay.
There are no questions about scientists that I can remember in there.
Have you written the quiz yet? Because you hadn't last week.
I have not.
I can't help
Yeah, it's written.
Nice.
And so remember, there's 3 zoomed all end of the chapter problems, 1 multiple choice, and then 1 question from what chapter?
7.
No,
No.
there's
13.
Yeah, chapter 13 is our review in the equilibrium from 55 to 65. Yep. All right, well, let's take this one on, and we're going to finish this. Again, this is going to go real fast. So, atomic radius is our next property. Last week we talked about ionization energy and then electron affinity. Ionization energy has a real clean trend. Well, pretty clean. There's some oddballs there, like from nitrogen to oxygen. And then electron affinity is not pleasant at all because it goes all over the place. Atomic radius, though, this one we can deal with. It's a very simple trend that happens. I do want you to keep in mind that measuring atomic radius has some challenges. How big is the atom? The radius goes from the center out to the outer edge. How do you know where the outer edge is of an atom? You don't have a ruler holding it up to the atom. The atom is too small. We don't really know where the outer electron is. So the way that it's measured is you take a sample, a very small sample of a substance in the solid phase. Sometimes you have to cool it down really, really cold to get it to be a solid. And then you shine X-rays at it. And you can pick up where the nuclei are because the nucleus is so dense that it will absorb the X radiation. But the X-ray goes through the electron cloud. So when you get this film with all these dots on it, you just measure the distance between the dots and you do some extrapolation. And it will tell you the distance between the 2 nuclei. And just cut that in half. That would be the radius of one atom. Now, one of the complications is if you have something that's diatomic, that means the 2 atoms are bonded to one another. And the radius is not a true radius because there's a bit of overlap between these 2 atoms. So for diatomics, this process does not work out well. In fact, I don't even know how they find the radius of diatomics. Maybe. Okay, so now what happens to atomic radius as we go across a row and down a family on the periodic table? That's what's next.
As you go left to right, it gets smaller. As you go down, it gets bigger.
Yes, very nice. All right, would you advance the slide? Are we good with that? Hold on. You're good? Okay. This is a representation, a relative scale of the sizes of atoms. We see where the biggest atoms are. They're over on the left and farther down. The smallest atoms, oh, the smallest, little baby helium. Look how small and sweet that is. Now, as we go, choose any row on the periodic table. The atoms start big over on the left, and they get smaller. I want you to only focus on the first 3 rows of this thing where we're only really looking at the main group elements. You will not be asked about anything in the D's as far as trends go. Because when you look carefully at this, you find in here, there is some shrinking and then growing before ultimately they start shrinking again, right? So I only want you to focus on the first 3 rows. Across a row, atoms are getting smaller. Why do atoms get smaller as we go across the row? Well, as you go from one element to the next, the nucleus is getting heavier, there's more protons. It draws that outer cloud in more. Even though, yeah, we are adding electrons too, that whole energy level of electrons is brought in more tightly toward the nucleus. That's what it says down here to rationalize why this phenomenon occurs. Why do atoms get smaller? This is a theory. Not really a way to prove this theory, but that's the best explanation that physicists and chemists can offer for why the atoms are getting smaller. Because the nucleus is getting more positive and drawing that outer electron energy level in more tightly. And as soon as you start a new energy level, well, that has to go on the outside of the previously completed energy level, and so it's going to get bigger again. We good with that? Spencer, let's go on. Now the same picture is on the next slide, but this one refers to what happens down a family. And down a family is pretty obvious. As you increase another energy level, those outer electrons are farther out from the nucleus, and so as we go down any family, the atoms are getting bigger.
Where?
I see it. That's the red one.
Oh, this one down here? Does that mean I should feel guilty about stealing the picture?
Yeah. Well, no, you cited. That's why it has a watermark.
Therefore, you're good.
I just copied and pasted with no remorse at all. But I'm glad they kept their own.
Remorse. That was a good one. You'll get it in a second. Because he'll realize
That's my last name?
Yeah.
Wow, that was a good one.
Your sarcasm is not needed. Thank you.
Mr. Moore, how do you communicate? By Morse code?
Alright, that's enough.
That's enough of that.
Alright, that's enough. Stay in the back of the car.
I feel bad.
What were we talking about? Oh yeah. So there's a word in here that I want to focus in on, and the word right is in this last line. The outer electrons, as we pile energy levels on top of one another, the outer electrons cannot feel the nucleus like the inner electrons can feel, because the outer electrons are shielded from it. What that means is the inner electrons, they have more access to feeling the nucleus because they're closer to it. There's not as much blocking them. The more energy levels you have, the more the outer electrons feel kind of blocked out. The next slide I have a, are we all done writing this one? Spencer, go to the next one. This refers just to the shielding effect. There she is.
Oh, we're never getting back together.
Well, it doesn't matter what she's singing. Look at all the people in the audience. Why are their hands up?
So they can touch her.
So they can touch Taylor Swift and go home and say, I touched Taylor Swift.
I did, and
I
so
never watched
did.
this.
I really
And
did.
do you remember that?
Yeah.
Yeah, like it was yesterday. It was an amazing experience. Now that's what these people, maybe this one of these hands is yours.
Right there in the
And look how happy she is, right? Taylor Swift represents the nucleus.
Look at that product placement. That water bottle. That's not on the picture.
Okay? So anyway, all these people represent the inner electrons. They have the closest access to it. How do these people out here feel?
Bad.
Yeah, not so good, right?
Well, they're still in a Taylor Swift concert.
And they can go home and say, man, I was like 10 feet away from Taylor Swift. Not even. 5 feet from Taylor Swift.
But I didn't touch her.
Dude.
But I didn't touch her.
I smelled Taylor.
These are like the outer electrons. Oh yeah, they're being pulled by the nucleus. But can they feel the nucleus like the inner electrons? No way. And so that's what the shielding effect represents. Yes, kind of. Shielding effect. Yeah, they get in the way.
Have you ever met Taylor Swift? You need to.
Oh, we've got a lot of Taylor touchers in the room.
Stop that. That sounded weird.
Well, good memories.
Maybe now I want to talk about Taylor Swift.
Sounds good. All right. So anyway, for the next periodic property, we're going to go on now, and we'll look at electronegativity. Spencer, move on. The electronegativity will be the last official trend that we'll worry about. Electronegativity is defined up here. When two atoms are bonded to one another, they kind of overlap their energy levels of electrons. And then the two elements, they try to yank on the electrons. They want